I guess we can slowly start. I was waiting for a bit so that everyone can join, but I guess we can just start. Let me share my screen first. Let me see. So do you see the speakers one or the? It's okay. Okay, nice. So hello everyone. My name is Mert. Today I'll be talking about our recent work with Jasper, Valla, and Anton on how to basically tailor arbitrary energy phase relationships using tunnel junctions, Josephson tunnel junctions. You can find a link to the, wait a second, let me use the pointer as well. You can find the archive preprints with the following ID, and let's start. So let me tell you a bit about Josephson junctions first. So when we say Josephson junctions, we can mean either a tunnel junction where you have two pieces of superconductor, let's say left and right, connected by an insulating barrier in between. And in this case, a Cooper pair, which we denote by these like two dots encircled by this dashed line, can travel from, basically travel from left to right via a process known as Cooper pair tunneling. So, and the current phase relation of such a tunnel junction in which where you apply a phase bias between two superconductors, you can basically have a supercurrent flowing in the system, and the current phase relation of such a tunnel junction would be basically sinusoidal, as you can see here, and its energy phase relation would be a cosine-like dispersion. So this is the tunnel junction version, but we also have another Josephson junction, which is known as an SNS junction or an Andreev junction, in which, again, you have two pieces of a superconductor, left and right, which can host Cooper pairs, as we know. But then now in between, instead of an insulator, we have a normal region, which can be either a metal or a semiconductor, basically anything that conducts, okay? Now, unlike the tunnel junction, which we denote here or which we depict here, the Andreev junction or SNS junction can mediate, transfer of Cooper pairs between left and right via a process known as Andreev scattering, unlike Cooper pair tunneling. Here, for example, you can see that we have a Cooper pair on the left. And then what you can have is that an electron basically can travel within the junction, and then it Andreev scatters into a hole, and this way you form a bound state. And this bound state is known as an Andreev bound state. And the energy phase relation of such an Andreev bound state is given by this equation. So here delta is the superconducting gap and tau is the effective transparency of the Andreev junction. And phi is the phase difference applied similar to the Josephson tunnel junction. And then what you can see as a difference that I would like to draw your attention to is that the tunnel junction contains a single harmonic. Basically, it's just a cosine-like relation, whereas the Andreev junction has all sorts of higher harmonics depending on this transparency. Okay, so now let's proceed. So in this talk, my goal is to use the tunnel junctions, this one, which is denoted by this circuit symbol, to basically engineer arbitrary energy phase relationships. And we denote this arbitrary energy phase relationships using this circuit symbol, thanks to Anton. And then I hope this gets stuck so that everybody can use this. And then the idea is that we would like to generate arbitrary energy phase relationships depending on what your application is. So whether you want to engineer protected qubits or any type of nonlinear superconducting devices, etc., etc. It really depends on the application. But in this talk, I'll be mainly focusing on designing a superconducting diode using only tunnel junctions. So Then let me give you a bit of introduction on, a very brief introduction on a superconducting diode effect. By the way, I forgot to mention, but then at any time you can interrupt me if you want to ask a question by unmuting yourself or raising your hand. I'm not sure if I will see if somebody raises hands, but you can just unmute yourself. So, okay, coming back to the superconducting diodes, superconducting diode is a device, is a non-reciprocal device that features unequal supercurrent in opposite directions. Let's say that we have a two-terminal device, just like a normal diode we know from electronics. So it features different critical currents in opposite directions. So which we denote as IC plus is not being equal to IC minus. How to achieve such a case is well studied. And in this case, to achieve this condition, you need to break both inversion and time reversal symmetry. Okay. And then a superconducting diode is basically identified by its efficiency, which we denote by basically the difference, which we actually calculate by having the difference between the critical currents in each direction. A current phase relation of a superconducting diode would look something like this, where IC minus is this like negative part, that's the critical current in the opposite direction, in the negative direction, let's say, and IC plus would be the positive one, which will be the peak of this, basically the top of this peak. Okay. So, but then you can even see it from here that such a current phase relation in general would require you to have all sorts of high harmonics. Okay. So in principle, to be able to design such a current phase relationship, hence a superconducting diode, we need to be able to get higher harmonics from our system. But if you remember that the tunnel junction current phase relationship and energy phase relationship, it only contains a single harmonic. It's cosine-like. The energy phase relation is cosine-like. So using just single Josephson tunnel junctions wouldn't be enough. And in principle, if you also remember the first slide that I showed you, that Andreev junctions in principle can produce higher harmonics depending on this transparency. So that brings up the question when you consider this. In literature, you can find that some tunnel junction circuits, this Josephson tunnel junction circuits, can actually mimic Andreev junction properties. We actually studied this correspondence in the literature in this paper. You can check it out. But then that brings us to the question of whether Josephson tunnel junction circuits can also generate higher harmonics, maybe. So now we are asking ourselves this question. And then our answer is that, surprisingly, yes. So what we do is we basically take two tunnel junctions and connect them in series. These are well in the classical limit, so there is no charging energy. Then if you solve for the Kirchhoff law, basically applying current conservation, you'll see that the overall energy phase relationship of two tunnel junctions in series would actually give you the same identical energy phase relationship of an Andreev junction or an SNS junction, with the overall energy scale being the sum of the two Josephson energies of the tunnel junctions, and the transparency is given by this relation. And then you can see that by basically choosing EJ1 and EJ2, the Josephson energies of two tunnel junctions, you can actually change the transparency and the overall energy of your circuit. So on the right, you can see that by changing different EJs, you're varying tau, and then using tau, you can generate different harmonics or higher harmonics. So, okay, now we have a way of generating the higher harmonics that we like. So, but then what else do we need? We need to break the time reversal symmetry, because as you can also see here, then without breaking time reversal symmetry, the critical current in both directions is equal. So we need to make them unequal. And the question is how? So now you can see that if you take this as the building block of our system, and if you connect them in series, what you can do is you can apply a magnetic field. such that it produces flux between arms. So I need to elaborate a bit further on the device. So first of all, we consider this as a building block. So we denote every two tunnel junction in series with this double triangle. And then, as you can see, we connect them in parallel. And then the varying sizes of the triangles would mean that I have different EJs and taus for each arm. And then finally, I basically form loops between the arms because I have I can place the arms at different spacings, etc. And then at the end, I can apply a phase difference across these two terminals. So this is really creating a Josephson tunnel junction array, but each arm is basically two tunnel junctions in series, which is an effective SNS junction, which is giving us effective SNS junction EPR. And the phase difference is used for breaking time reversal symmetry. But then our argument is that basically if we use such a device, a tunnel junction array, we can actually get any kind of energy phase relationships, given that we solve for EJs, taus, and the phase differences that give us the target energy phase relation that we like. So this can be anything like a superconducting diode energy phase relationship or any other type of energy landscape that we like. But the problem is, so this is an optimization problem, but the problem is not so simple. So if you write down the overall energy phase relation of such a tunnel junction array, it would look something like this, where EJs are the overall Josephson energies of each arm, and U has this phase dependence. We remember it from the SNS junction. But then if you try to optimize all EJs, taus, and phase differences to give you the desired energy phase relationship, the target one, then you would see that this is highly nonlinear optimization problem. So what can we do in order to simplify this so that we gain understanding of the response of the tunnel junction array? So first of all, we can consider a much simpler problem by basically setting all the effective transparencies of each junction to be equal. And secondly, we can say that all the arms of the tunnel junction array are equally spaced, such that their phase differences will be given by this equation, where n, the capital N, is the total number of arms in the tunnel junction array. If we assume these two conditions hold, then we'll see that getting the overall energy phase relationship of the tunnel junction array being equal to the target one would be a linear optimization problem. And in fact, if you try to solve for the EJs, because that's the only remaining unknown in the problem, it's just given by this inverse discrete Fourier transform. Because this equation now becomes a convolution if you basically assume these two conditions hold. But we have another problem, because in principle, if you try to naively calculate the inverse discrete Fourier transform of this equation, then the Josephson energies can be negative, because this is just a discrete Fourier transform and it can be negative. But we know that the Josephson energies must be positive, except for these pi junctions, which we don't consider here. So then we clearly need to solve this problem. Therefore, we basically took a look at the problem at hand closely. So, and then we realized that actually, since this problem, this optimization problem becomes a convolution, which we have a periodic function multiplied by the Josephson energy distribution of all the arms, actually shifting it by a constant will not change the result, because this is a periodic function and I can multiply a periodic function with a constant, and the integral over a period would basically give you 0. And in principle, we can highlight what happens when we shift all the junction, as you can see in this figure. Basically, so the yellows are the ones that we the Josephson energies of our algorithm that our algorithm returns. Okay, and as you can see, this is the zero line. So some of the Josephson energies, as you can see, they are clearly negative. Okay, so we want to make them positive, at least, or zero, like the minimum one can be zero. So what we do is we shift all of them by the same amount, as you can see, such that the most negative one is now zero, which amounts to shifting everything by this constant E0, such that there is no negative Josephson energy in the problem. And the yellow one actually is the energy phase relationship of the set of Josephson energies with the negative Josephson energy included. And the blue one is the shifted one. And as you can see, they're actually quite similar. And it's just because of this relationship. But now we have 10 arms actually. Okay, so this is not very close to the continuum limit, but it works. And this is the resulting current phase relation. And you can see that, okay, it has changed somehow, but not drastically. And if you had more and more arms, then the change will be invisible. Okay, so now it seems that our algorithm works. So basically we can just find the Josephson energies by taking inverse Fourier transform. It works. But of course, the question becomes, can we do better? So therefore, we take a closer look at our current phase relationship of the superconducting diode made out of this Josephson tunnel junction array. So here, just like you need to remember that we are taking a discrete Fourier transform of a highly sharp featured function, right? It is a superconducting diode, so it has this Dirac delta-like peak. And then if you want to take the discrete Fourier transform, you would surely get some ringing effects. And that's just because of this Gibbs oscillation phenomenon. And there are ways to get rid of this Gibbs oscillation, which you can actually see from this figure. Basically, this 0, 1, 2, 3 denotes our regularization to remove the Gibbs oscillation, and 0 means that there is no regularization. And actually, you can see that the current phase relation of our tunnel junction array without any regularization has this oscillation. You can also see it here. So this is in principle an artifact of this inverse discrete Fourier transform. And then if you adjust the Fourier coefficients such that these oscillations die out by applying the sigma regularization, so this is the first degree, then you can actually get rid of this ringing effect. And furthermore, you can also increase the efficiency of the superconducting diode. Although it looks like this peak, actually the maximum of this peak is decreasing, the efficiency is actually increasing just because I'm actually decreasing the negative critical current. And of course, there is a limit to a degree where you apply and then the efficiency doesn't increase any further. And in this case, it's the second degree. And furthermore, one can also check that one can get higher and higher efficiency if you have more and more arms. You can understand this as follows. If you have more and more arms, it is much, much easier to fit a function using the Fourier coefficients of single arms. So therefore, if you were to have, let's say, infinite number of arms, then you would get an ideal diode. So now, I think this overall shows us that if we solve the constraint problem, the linearized problem, by assuming equal transparencies for all arms and equally spaced arms, then you can basically engineer any kind of energy phase relationships. But that's not the whole story, because we know that we are solving a constraint problem, but now we can solve the unconstrained one as well, just to understand whether we can do something better. But of course, in this way, we lose the understanding, but the understanding we already got from the Fourier transform. So now, to solve the unconstrained problem, we use a stochastic global optimization and solve for all the EJs, taus, and arm positions such that it's giving us a different phase difference distribution. Here, as you can see, so this is 5 arms. So 1, 2, 3, 4, 5. And then with blue, we are denoting the Josephson energies of each arm. And with yellow, we are denoting the effective transparency. And with this configuration, and then the dashed lines denote the equally spaced arms. And the position of the dots actually tell us about the position of the arms, such that it's giving us a phase difference that is proportional to the distance between. So if you were to have such a configuration of parameters, you can actually get a superconducting diode efficiency that is much higher than the constrained one. And furthermore, since we are using a stochastic optimization, we can actually allow for junction parameters to vary. So let's say that we have a design, right? So, but in principle, one needs to go and fabricate this. And then, of course, there can be variations in the junction parameters in experiments. So we want our effect to be robust against these variations. So here we allow for 2% of variations in junction parameters, EJs and taus, and the resulting diode efficiency distribution is something like this, where the mean efficiency is something around 72%. So, and then this is the resulting current phase relationship of the clean one, let's say. So we see that the unconstrained problem is actually much richer than the constrained one. So now having two ways of solving the problem, the constrained and unconstrained one. So why don't we compare everything? So here in this figure, we are actually comparing 3 different optimization methods. For a clean system denoted with the circles, meaning that there is no variation in junction parameters, there's no disorder, there's no noise. And the ones with 2% disorder, that is denoted by the rectangles or the squares. Blue shows the differential evolution algorithm, which is our stochastic optimization. LS means least squares, which I didn't explain here, but it is in a similar spirit of a discrete Fourier transform because it's also solving a linear problem. And finally, the red one is the discrete Fourier transform. First of all, you can all see that the problem, like the efficiency, is increasing as the number of arms increasing, just like we understood from the previous slides. Of course, the unconstrained array basically performing much better than the constrained ones, the linear problem. But it is numerically very costly to simulate like large n values, so that we have to truncate at a finite n, like a very small n, compared to the least squares and discrete Fourier transform, which is actually quite fast. And then finally, you can see that discrete Fourier transform is actually underperforming a bit at low n compared to the least squares because it's much of a constraint problem, but it's more resilient to disorder because least squared is actually, it's an overfitting. So which concludes that, this concludes that actually tunnel junction array is capable of performing much better, but then it comes with a numerical cost. So what I mean is the stochastic optimization gives us better results, especially for the tunnel, so for the superconducting diode effect. But as I promised, superconducting diodes is not the only thing that we can achieve. So as I said, the tunnel junction array can actually produce any kind of target energy phase relationship. And here, for example, I'm depicting 2 different energy phase relationships. Basically, the one above is a square barrier-like energy phase relationship. And the one here is a triangular barrier-like. And as you can see, with increasing number, because this has very sharp features, so you basically require a lot of arms to simulate, to be able to match these sharp features. But it gets increasingly better for increasing number of arms. On the other hand, for example, if you have a triangular one, I mean, it's performing really good, even with these number of arms, because it doesn't have that many sharp features. Okay, so we can simulate square and triangular barrier energy phase relationships. What's more is that you don't need to optimize for the whole phase range between 0 and 2 pi. You can actually focus on a given range as well. For example, here with the yellow dashed line, I'm depicting the target energy phase relationship that I would like to have, which is defined up to these points in the phase space. You can see here. And the blue is the overall EPR response of the tunnel junction array. And as you can see, even though so it behaves very differently outside the region of interest, you can match them pretty nicely in the region of interest. And since this energy phase relationship doesn't have sharp features, you can actually get this kind of energy phase relationships with a couple of tunnel junctions or couple of arms, because you don't need that many higher harmonics. So, okay, to conclude, I showed you that if you connect two tunnel junctions in series, you get an energy phase relationship of an SNS junction with arbitrary transparency that you can basically change by changing the Josephson energies of the tunnel junctions. Then if you connect them in parallel and pierce with a magnetic flux, then the resulting array would basically allow you to tailor arbitrary energy phase relationships. And I showcased this by designing a superconducting diode and some various other energy phase relationships. So what's next would be to include junction capacitances, because what I showed you is basically the classical limit, where in principle you can have small but finite charging energy of the island between the two tunnel junctions. And furthermore, I showed you a two-terminal junction. In principle, you can have multi-terminal generalization of such a junction. So this we can investigate. And finally, we can use this tunnel junction array to design energy phase relationships for maybe protected qubits or maybe something more interesting. And with that, I would like to conclude. And by the way, I would like to say again that this is the paper, this is the preprint, and this is the source code that you can check it out. And with that, I would like to conclude and thank you for your attention. And if there's any questions, yeah.
Yes. Thank you very much. So, so one question I had is like, for what is the fabrication accuracy in Josephson energy that you require for engineering, or say if it comes out like 10% different, how would you correct for that?
So as I was trying to explain, maybe this is what you mean. By the way, I'm not sure, but yeah, okay, sorry. So here, for example, we were optimizing for Josephson energies such that when you have plus minus 2% difference in the junction parameters, that would give you a robust efficiency. So I would say plus minus 2%. That's the ratio that we, or the degree that we took, basically.
Okay, yeah, thank you. So that's clear. So follow-up question. So yes, as you know, so the junctions that we observed, the normal tunnel junctions, you always find higher harmonics intrinsically already, right? Like 3%, for instance. How would that affect your analysis? I know that in principle you can take care of it by engineering, but if you require like 2% in EJ and you get like 3% of 2% EJ2, EJ3, and so on. So what's the idea behind it?
I guess in that case, if the original energy phase relation of a single tunnel junction have higher harmonics, then the correspondence to the SNS by having like two tunnel junctions in series would be gone, because you would have in general like basically like cross terms, etc. But then in principle, that doesn't stop you having like basically higher harmonics also for the two tunnel junctions in series. Only that the form will change, so it won't look like the energy phase relation of a SNS junction. But the idea would still be the same because it's going to be a periodic function in the end.
Okay, I see. Yes. So in principle, you would also probably would be some co-evolution, right? Where you would probably engineer a device and like do some spectroscopy to see what the EJ and JMs are, and then engineer based on this, like what next Josephson junction do you need, or something like this.
Yeah, then you need to characterize what this is, right? So you can always find, so this would be also a periodic function of the phase difference, but it won't be something like this. So you need to characterize this, and then you need to be able to know its Fourier decomposition. But in principle, that would also have higher harmonics. So I don't see any like conceptual difference.
Okay, thank you very much.
Thank you for the question. There's something in the chat. Yes, Barish.
Hi, Mert. Great talk. Thank you very much.
Thanks.
I have a question, and I will explain the background of my question afterwards. The question is, can you optimize for high diode efficiency and high critical current? You're partly doing this by raising the Josephson energy to the 0 and above 0. And the background to this question is I'm working on topological planar Josephson junctions, and the diode effect on those is non-zero in a wide range of parameters, but the efficiency shoots up when you are going through a topological phase, partly because the denominator in that efficiency formula is going down because your critical currents are going down. In at least that system, getting a high efficiency and a high critical currents happens to be two separate related things. So in your system, can you optimize for a high diode efficiency and a high critical currents?
Well, I mean, in principle, mathematically speaking, it's very simple. I'm just trying to find it.
You just increase the Josephson energy, I suppose.
Just like if you multiply everything by a constant here, it will automatically increase the critical current, like mathematically speaking, of course, without changing the efficiency. But now the problem is that because this can be in general multiplied by any constant, but now the problem is, I guess, that the fabrication, like how much of a Josephson energy that you can have in real materials.
You're limited to the smallest. You're limited to your fabrication and the weakest link on your fabrication in terms of
not the weakest link, though, mind you. So it's not the weakest link. So because it's the overall, so it's the sum of those. So not the weakest one.
Okay.
But then again, it is limited to the fabrication or the real material Josephson energies.
So technically, these are all in parallel. You can have the same thing, the same well-designed system, but have like eight of those big, huge systems in parallel that increases your critical current. Is that the thing that we are getting here?
Yes.
Okay. Well, in that case, thank you.
So because they will add up.
All right.
Yeah, thanks for the question. Any other question?
Yeah, actually, sorry, I do have one more question. But maybe I just didn't get it correctly but at some point you said you want always positive EJN, right? So is that only like, so it's easier to work with, or do you have some fundamental idea behind this?
Can you repeat the question? Maybe I...
Yes, exactly. On this slide, there you say problem EJN can be negative. So the question is, basically, I think, why is this a problem?
It's just because if you remember what EJ means here, it is actually the sum of the two. And then in principle, these EJs are positive.
Okay, so it's like the main Josephson energy. Okay, yes.
Yeah. It's the
I guess
total.
I always had like the harmonics in mind, right? Where it's like EJ2 is negative, EJ3 is positive, EJ4 is negative.
Oh, no. Yeah. So this N actually means the nth arm. Sorry for not being clear about it.
That was probably too much bias. Yeah, thank you very much. Thanks a lot.
Yeah, but thanks for the question. Help me clarify. Any other question or a remark? Okay, I guess not. In that case, thank you all again. And if you have any questions or any ideas, or if you want to make your favorite Josephson junction and don't know how, just shoot me an email.